Well, today we're going to talk about the last piece of our energy chapter. We're going to talk about power. Well, we've heard of power. Power comes from engines. Power comes from our power company, from the electric company. But it's defined in dynamics as power, the instantaneous power is du dt. And we remember that work, which is U, is equal to the integral of FdS. If I differentiate both sides, I get du is equal to FdS, and I can plug du back into here, and then I get power is equal to F ds dt, which is, you recognize ds dt is velocity. So we'll find out that power is equal to the force times velocity, and that's the instantaneous power. It happens at that instant. All right, so back on our same kind of analysis that we did with work before, only the forces in the direction of travel contribute to work, so they are the only ones that contribute to power. So anyway, perpendicular forces do not do any work, and we need to recall that. Power is a scalar. It's a product of force and velocity acting in the same direction. Sometimes, in fact many times, we're concerned about the work that happens over a particular period of time. So our change in work, or delta work, or the amount of work over whatever time we're considering, and that's equal to the average power. And if forces and velocity are steady state, then work is simply force times distance. If we can put all those into one kind of view, then we can say that power can be defined as force times distance over a time, which is equal to work over that particular time, or is equal to force times velocity. And we may find any of those expressions useful in solving a problem. The units we'll consider on the metric system are joules, the units are in watts, and a watt is a joule per second, and a joule is a Newton meter. So any one of those expressions works. Most often we consider watts, or we call it watts. In the English system, the units are going to be foot-pounds per second. And just a conversion factor that might be very handy, in fact it is very handy, is that often we're looking for the amount of horsepower, and 1 horsepower is 550 foot-pounds per second. Converting that to the metric system is 746. All right, so let's talk about the general case. Is most often we're looking for some power required. And an engine or a motor has to do some work over some time, so we're looking for how big or how much power you might need. It makes sense that if you try to do some work in a faster period of time, that you'd need more power. So steady state power often is required to overcome friction or to climb a hill. However, to accelerate requires more force, and therefore more power. So we'll do a couple of examples here illustrating steady state and acceleration. All right, so the last thing we want to introduce as far as a concept here is the concept of efficiency. And power, the efficiency, and this is the Greek letter epsilon, is power out over whatever power in. It's also the energy out over the energy in. And we may look at different kinds of expressions for these things, but pretty much is whatever you have to put into your system is in the denominator, what you get out is in the numerator. And when you usually have to put more in to get something out, meaning that epsilon or efficiency is always less than 1. So if you invert those and you get efficiency greater than 1, then that's obviously an error. All right, if the system is an engine or a motor, what we'll look for is whatever is required from the engine and times its efficiency, and that's the power that does the work. All right, and so then I've just restated my equations from before. Okay, now if something is accelerating, the force required is mass times acceleration, as we know, and the power is going to be force times velocity, which is going to be the mass times acceleration times velocity, and we'll find that useful in a coming example. Okay, so let's talk about a simple kind of example here. We got a car trying to go up a hill. And you can see that the hill is a 1 to 10 ratio here. And let's say that the car weighs 3,500 pounds. He's got a 75 horsepower engine, or at least that's how much we're getting out of the engine. Efficiency of 0.75, and the question is how fast can he go up the hill? Well, this is a constant speed problem, so the only thing that we have to do is overcome gravity. So if I look at our little free body diagram, I'm going to say that we have an mg sine theta going down the hill and a force going up the hill, and because we're in steady state mode, we can say that the force required to go up the hill is equal to mg sine theta. The angle that we're looking at is a tangent of 1 over 10, so it's 5.7 degrees. So the force is equal to mg sine theta, which is 3,500. That's our mg. That's the weight is mg. Sine theta is that. And we get 348 pounds required to go up the hill. If I look at now my power equation, I can say that the engine puts out 75 horsepower. There's a conversion factor of horsepower to foot-pounds per second, that's 550, and then the efficiency of 0.75. What I need to get out of that is my 348 pounds times the speed that my maximum that I can go up the hill. Solving that for V, I can see that that's 88 feet per second, which is about 60 miles per hour. Well, it's exactly 60, well actually it's 88.0 seconds would be 60 miles per hour. So. All right, and then just to make a little more of an illustration, how much power is required to go up the hill faster? Well, it's linearly scaled because everything else here is the same. The only thing we've changed here is velocity. So if I put a bigger velocity over there, it takes more horsepower. So anyway, that's linear. You can go up faster, but it takes more horsepower. All right, how about accelerating? Here's a car that's accelerating on a flat surface. Same car, 3,500 pounds. However, we're going to accelerate on at 10 feet per second, and we want to find out what power is required at 30 miles per hour or 44 feet per second. Okay, so again, force is equal to mass times acceleration. Well, the mass is 3,500 over 32.2. The acceleration I asked for was 10. So what is coming out of my engine then? I got my engine, horsepower, times my conversion factor into foot-pounds per second, times my efficiency, and I get my power out required, which is force times velocity. So the force I need is from my mass times acceleration, and then the velocity I'm looking for is 44. And so it takes 115 horsepower, 116 horsepower to accelerate on a flat surface. If I were to try to accelerate at the same acceleration at a different constant speed. So here I was doing it 30 miles per hour, but if I do it at 60 miles per hour, I have to put 88 feet per second in there and basically doubles the horsepower, which again, it linearly scales as we might expect. Now in these two examples here that I just did, the previous page and this one, I wasn't considering air resistance. However, if air resistance is considered, it does make it more complicated. And where did I put my paper on that? Here we are. Lost my paper. All right, so if air resistance is considered, then it does become a little more complicated. So let's say that the same car, here are my specs on the car. I'm going to accelerate at 10 feet per second on a flat surface. I weigh 3,500 pounds. I'm going to evaluate it at 88 feet per second or 60 miles per hour. I have a mechanical efficiency or inefficiency of 0.75. What I have is air resistance considered here as a force of drag is equal to 0.02 times v squared. If you recall, drag in air and most fluids is a relationship some constant times the velocity squared. All right, so let's sum our forces in the x direction and see what we get. I have the force required to move the car forward, which is coming from the engine, but I have a drag force slowing it down, and that's going to be equal to my mass times acceleration over here. So I solved this for the force of the car, meaning the force required from the engine, or the work required out of the total system is going to be equal to, I solved that for 1,087 plus 0.02, which is that term, 0.02 v squared. All right, so here's my power from the engine, power of the engine, times my efficiency is equal to force times velocity. Well, this is my total force, and then I bring it down here, and I'm going to say that the horsepower required times my efficiency times my conversion factor of 550 foot-pounds per second per horsepower is equal to my total force times velocity. All right, so then I just kind of put everything over here, and I want to separate what happens from the engine to just to do the acceleration, and this piece is to overcome the air resistance. So what we'll do this is solve this for HP and bring these things over here, and the horsepower is 1087 times 88 divided by those two things, and you can see that that's the same as what we had before, 231 horsepower required to just do the acceleration. However, the force or the power required to overcome air resistance is a function of now velocity cubed, and so I can put that 0.02, multiply that by 88, and I get 88 cubed divided by the same conversion factors and inefficiency, and it looks like I need 33 additional horsepower to overcome air resistance. So it does make the problem a little more complicated, and you'll find that the air resistance is a function of velocity cubed, and as this goes forward, if you were to try to go faster, you're still going to have this go up linearly with speed or with velocity, but the air resistance goes up by the cube of velocity. So very soon, the air resistance becomes the limiting factor in trying to go accelerate on a flat surface. Okay, last couple of things I want to mention here. That just as an illustration, again, power is force times velocity, or work over time. Let's say we wanted to raise a 100 kilogram mass from one position up to another position. We want to put it up 2 meters, and we're going to do it over a 5-second period. So we know that power is equal to the work divided by the time. So what work am I doing? I'm taking mg and raising it up a height h, so mgh over that time. And so my mass is 100 kilograms, g is 9.81, I would raise it 2 meters, so that's the total work that I've done. And if I do it in 5 seconds, then it takes 392 watts. However, if I do it in a longer period of time, in other words, I slow it down, it would make sense that I would require less power, and indeed, it's linearly scaled over the time, and so I'd only need 196 watts. Obviously, if I wanted to do it faster, they'd require more power. Well, escalators and conveyors are good power problems. Often we're looking for the power required from the motor, or sizing the motor that's needed to be able to move a particular load. And recall that we're going to use the same two equations to do the same problem twice. This is going to be our power is equal to mgh over time kind of display. And we're going to say the total weight moved and whatever time it takes, multiply it by the height. We could also look at force times velocity, and we're going to say that the force required to move a particular load is the mg sine theta, and we're going to multiply it times the velocity. So let's just look at our conveyor. Let's say we have it loaded up with some number of pounds per foot or something like that. We're going to move it at either a sine theta, it's going to go up over a particular time, it's going to raise up height h, we're going to have some velocity of our conveyor. So let's just say our conveyor's and let's just make sure we got our free body diagram straight, but we could say that we have an mg and an mg sine theta, mg sine theta going down the hill, which means that we have the force going up the hill that you'd need required here. That's what this mg sine theta is all about. All right, let's say we got our conveyor. It's 10 feet long, and the load is 10 pounds per foot, which means that the total load is going to be 100 pounds. Let's say our speed of the conveyor is 1 foot per second. Let's say that theta is 30 degrees, which means if this is 10 feet long, then our height total is 5 feet. The power required using the weight moved over time. Oh, no, let's see, I did this one first. Let's say that's the mg sine theta times the speed. We have a total package of 100 pounds at any particular time. The total weight on the conveyor is 100 pounds. 10 feet times 10 pounds per foot. Times sine theta times our velocity is 1 foot per second. Multiply that out, 50 foot-pounds per second. Or we could use this relationship with total weight moved over the time that it takes to get up there times our h. And let's say that we have 100 pounds total on the conveyor. That's our weight moved. If we say that it's 1 foot per second and it's 10 feet long, we know that it takes 10 seconds to get from the top to the bottom. So that's 100 divided by 10, and our total h is 5 feet, and we get the same number. So anyway, you can look at these conveyor problems either way that makes sense to you, and we'll do some more in class.